So today we are going to continue talking about tries, and then after that we will go into this other type of kind of abstract data type, and this is the code I gave you. And I know I gave you a lot of code on here. We're only going to look at certain parts of it. I just kind of wanted you to have everything for now. We're going to talk about what a priority queue is. We've already talked about queues. We're going to talk about what a priority queue is. And calling it a queue is a little bit of a misnomer, but we'll get into the details of that as we go along. OK? Questions before we get going? Anybody concerned about the homework server being crashed last night? Yeah, so that's what happened. One student who will remain nameless was responsible, but it's no big deal. I think we've got it fixed. What we're actually going to do in the future, so what happened was the computer ran out of memory, actually. Like the homework server, which had like 128 gigabytes of memory, like this one process was like, give me all the memory, right? And it took it all. And then that decided it was bad. Yeah?
What was the student who will remain nameless doing?
I'm not exactly sure. To tell you the truth, it was just running their program in some, it was, honestly, it's quite easy to do. Let's say you have a loop that's, let's say you have a tree that looks like this. Let's say you have a tree that looks like this, where you have some nodes in here, and then some reason you're trying to insert or something, and somehow the left of this goes whoop, back up to the root or something, right? And you're trying to like insert, and you insert, and like you keep inserting, right? Not even a Stack Overflow. Actually, it was more, maybe it was, I'm not exactly sure. In this, that probably would, this one, if you're doing a recursive program, would probably do a Stack Overflow. Let's say you had a while loop and your while loop was wrong or something. And anyway, it's not the biggest deal in the world. It's just a matter of, we got to figure out how to make it so that if that happens, I don't have to contact whoever's responsible and say, hey, go kill your stuff, right? And that actually happened. So we're actually going to, in the process of writing a little script that we may do it for this, like next, like maybe in an assignment upcoming, how you guys will like give me a script that you've basically signed and says it's OK for Chris to kill my processes if they go out of control. The analogy is like if you're, well, many of you guys haven't had actual landlords yet, but let's say you have a landlord who has a set of keys to all the apartments, right? And let's say the water in your apartment breaks. The landlord can go into your apartment and like turn the water off, right? Like that's exactly what this is going to be. So it's going to be like, I'm going to be the landlord, and I'm going to like go in, but like the system will log it, so they'll know if I like go in and like screw with things I shouldn't be. Exactly. So that's that. Yeah.
Is there a way for you as the instructors to know when the server goes down and possibly like automate a system if the server goes down to email?
Well, that does have maybe, but probably not. It's probably possible, but the system administrators do get an email that says, hey, but they might be out at dinner or something. Who knows? It's not like they're like 24 hours a day monitoring this stuff, you know? So that is, I mean, not much we can do about it. But what it does mean is that I guess I should probably teach you guys how to like monitor your own code, right? But and to like make sure it's not doing this. But the easiest thing is probably to come up with a little script that if somebody notices it, one of the faculty members just goes, boop, kill. And then all your stuff gets stopped. So not a big deal. But it did kind of stop you guys from doing some work last night. But that was it. OK? Questions on that? That was what happened, by the way. I got a piece of anonymous feedback about the commenting for homework assignments. Like I said, lots of people got points off for poor comments. We haven't done a very good job of showing you what good comments are. OK, so that was good feedback. What we're going to do is some TAs right now are actually thinking about the best way to put out some guidance on what needs to be commented and how. OK, and we'll do that before Friday, let's say, and then you can update your own code if you need to. Retta.
Kind of on that same line.
Yep.
How much of the commenting that you guys put in, because you're telling us what the function should do, counts as commenting?
Well, it counts as much as, if it's there, don't take it out. The one thing you should take out, and some people aren't, take out the to-dos once you do the to-do. Don't leave a to-do in there, right? Because that would be that means it's still to be done, right? Once it's out, go, I can delete that. But I mean, most of the, you don't have to comment functions, full functions we give you, you don't have to go comment. But the functions you write, you have to comment. That's the biggest thing. And it does not have to be every single line, but there should be some comments interspersed. For instance, here's // the, one child only or whatever, right? If you're in the case where it's one child only, don't just like put the if statement in there. Write that you're talking about the case where it's one child only. That sort of stuff is what we're looking for. Just so that it's not like a blank function that or just a complete function with no comments. We have no idea what it does. But we'll clarify that, and I apologize that we haven't done that yet. Okay, Ben.
How about readmes? Have there been any problems with readmes lately?
No real problems with readmes. I mean, some people still haven't figured out how to actually make it so the readme is the right one. But otherwise, yeah, no other real big issues with that. If you've got specific comments and you're confused about them, email me. We'll figure it out, or stop by office hours. OK. Any other comments, questions on homeworks, et cetera? OK. Let's go back to talking about tries. Remember the other day we finished up and we said, OK, a try fixes the problem. Well, it doesn't really fix the problem. It finds a better solution for text words than a binary search tree, which in itself is not a bad solution. But we can do better than that. OK, we can do better than that. And what we ended up doing was we said we can end up picking out each individual letter of a word, bing, 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 and creating our 26-child tree called a try based off of each individual letter. OK, and that's the way it looks like this. And we showed a couple of examples there. Here's the example with all the words in it, right? We've got, in this case, fire, cow, red pit, corn, sand, day, snow, pits, and fish. OK, and Charlie the other day said, hey, what's the asymptotic complexity? And I said, let's hold off on that. But let's think about what the asymptotic complexity is for some of these words in here. OK? Question 1. How many nodes do we have to traverse to find if the word fire is in this tree? Try. How many, Ben? 4. We have for 1, 2, 3, 4, right? And you have to go down from F-I-R-E. OK, so that's on the order of what in this case?
The size of the word.
The size of the word. If we had supercalifragilisticexpialidocious, we'd have to go through 32, we'd have to traverse 32 times. But most dictionary words are under 10 or 11 characters, right? So as it turns out, OK, so in this case it's the word. What if I had 1 billion words in here? How long would it take to find if fire is in there? How many things? What is it? Still just the number of the word. So what's cool about this is we've broken the problem into, instead of worrying about order n being n the number of words, we are now on the order of whatever the word length is, right? And the word length, if we say it's definitely less than 15 characters for most dictionaries, right? Then the order is what? If we put 15, what does that really translate to? Constant, right? I mean, we ignore the fact that it's 15. It's constant. Yeah, Charlie.
But doesn't that assume that your implementation doesn't need to search for, so if fire had other letters that it needs to check, if there are other branches, but when you get to the I, it has to check for the R and the S.
Ah, very good question. Good point. Good point. So what Charlie's saying is, wait a minute. We're ignoring the fact that we might have to look through 26 different nodes, right? Depends on how you implement it. Let's think about how we implement that shift right there between the I and what comes the children of the I. Hold on one sec. Let's get somebody else who has an answer yet. Think about it for one sec. How might we implement the following node? 1, 2, 3, 4, 5, 6 times 26, right? How are we going to put that in the thing? And remember, it's fixed at 26. What do you think?
Well, so when we have a binary tree, we have the left and the right.
Sure.
Pointers. So in this, we can have the A pointer and the B pointer.
You could. Yeah, that might take up a little bit of space if you. That's not a bad idea. You could do that. It would be kind of a big, it'd be a big definition for a tree. There's other ways to do it, though. That's a very good idea. Go ahead.
Maybe an array with index numbers.
Yeah, I like that. Then array, it's 26, 20, that's 0 through 25. It's 26 long, maybe. And that's one way to do it. There's another one we've talked about, yeah?
Oh, I don't know if we talked about this, but you could use the ASCII value.
Well, right, and that's what we're going to use for this. There's another data structure we've talked about that we could do for these. Yeah? Q. Probably not a Q, only because we'd want to do it, like then you'd have to do this whole dequeuing to find the value. But we could do, yeah? A set would probably work. Set would probably work okay. How about just a linked list? How about just one node, right, that points to a linked list? We could do that if you wanted to.
But that would be an obnoxious amount of traversing, wouldn't it?
It would be a pretty obnoxious amount of traversing, yeah. Yeah, you'd probably. I mean, if you have like, if you're trying to search for z, like, oh, I'm asleep, right? Z, right? You'd have to go to the end, rip, and then it expands a bit, right? So I like this idea of using the array. What's nice about using the array is what Moretta's talking about. If we have, if the first one we know is going to be A and then B, C, D, E, all the way to Z, right? What were you going to say about that?
Well, all the letters have ASCII values associated with them, so you could do it by numbers, so like less than or greater than, and comparing the letters.
You don't even need to do less than or greater than. Anyone happen to, so there's this thing called ASCII.
Oh yeah, you can just subtract.
Yeah, there's this thing called, right, you just end up subtracting. So there's this, for people who don't know, there's this, the way we represent letters in the computer is through a code, basically. And the code says that it goes from 0 to like 256, and the letters are in there somewhere. In fact, let's see if this comes up if I do this like this. Yeah, there we go. Down here I have a, is this it right here? Yeah. I happen to have a little ASCII chart in here that's in one of my like widgets, right? And if you go down to A down here, A happens to be number 97. Okay, it happens to be 97. Okay, and somebody said over here, we're just going to subtract out that value. So if we want to, if we know the character, what is F going to be? Let's look at what F is. Boop. 97 plus whatever, yeah, 5, I guess. So F is, boop, 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 there we go, 102, right? So if we're looking for 102, which one of these guys is it going to be in, if it exists? How do you know? I see you're doing like 4. 5. How do you know it's 5? Yeah, you just subtract 102 minus, and watch this, the character A, right? That, if you do a character symbol, like the single quote, that means it's a character, char, right, which you might have done in other classes. One sec. The char A is actually under the covers, it's an integer, right? And the integer value is 97. So if you say the character we're looking for, right, in this case it's going to be F minus A, that will give us 5, which will tell us 0, 1, 2, 3, 4, 5. Yeah?
Couldn't you just do F minus A?
Couldn't you just do what?
F minus A.
Yeah. Well, whatever the variable is. Yeah, it's whatever the variable is. So if we're going through the letters, and let's say we write this for loop, and it says, you know, it goes through letters, and the variable name is Z for the, or let's just call it, I don't know, CH for the character we're looking at, right? It would be CH minus A, and that would be inside the brackets for the array that we're doing, right? And that will give us the position in here that it looks at. OK, somebody else quiet. Did you have a question, Becky? No? OK, question. And then
Do you need to wrap the character in braces, parentheses?
do you have to wrap anything in parentheses? No. Nope, you don't need to cast it, actually. Yeah, you don't actually need to cast it. If this is a character and this is a character, it will become an int, which is fine. Yep, you don't actually have to cast it. Yeah, good question. Ready, you had a comment?
Yeah, I don't think this would help here, but just curiosity. Since strings are just arrays of characters, are strings the sum of those character values?
No, strings are not the sum. They're each individual string. Here's how a string is laid out in memory. Okay, in memory, a string is like this. If I have a string hello, H-E-L-L-O, right? H-E-L-L-O, and then there's actually a little null character in there that tells you what the string is. This is all hidden from you in the string implementation, right? When you get to comp 40, for those who are taking comp 40, you will do lots of stuff with like inside the array. But it's basically just an array of characters like that. So each memory location has its own character. Okay. Did you have another comment? OK. All right, so that's how we're going to do this. Yeah?
So then once you have that like initial array, then
Yeah.
would you then
Yeah, maybe this array is, so this array is maybe not going to be characters, but it's going to be nodes. It's an array of nodes.
Okay.
And if it's null, it means the character is not used yet.
Okay.
That makes sense? I think that's a good idea. So this is like a node, 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 all the way over there. And then if it's null, it means, hey, I don't exist yet.
So
Or if,
each node would then have its own array.
and then each node would have its own array if it existed. Yeah.
Okay.
So by
Yep.
nodes, do you mean pointers to nodes?
It could be either, to tell you the truth, but it wouldn't be null. If it was just if there were individual nodes, then it would be.
But then it would be, wouldn't it be infinitely large and we would run into it?
No, it wouldn't be infinitely large. It wouldn't be infinitely large because you would have to make sure that you would have. Well, let's see. That's a good point.
Because a node can't have another of itself inside it.
Yeah, that's a good point. A node, it would have to be a node pointer. Yeah, you're right. It would have to be a node pointer. Yeah, good point. OK, but we'll get into more details about this. In fact, next week's lab, you'll see this exactly on here. OK? All right. Got other questions on that? We're going to kind of run through these, which is more or less the same stuff on here. So the cost of looking up the word is fixed. You never have to go deeper than whatever word length you're talking about, which is awesome. OK? It means that you are dealing with a constant time lookup, which is our like holy grail. It's exactly what we were always looking for, right? Constant time. This is a great way to get constant time behavior. Okay, it's not perfect because there are memory constraints here. I mean, if you have a lot of different words, you can end up running like each letter has 26 other letters associated with it, basically, right? And then you have to, you kind of have to worry about a little bit of space, but it's pretty good though. Okay, not based on how many words you have. You can have the entire dictionary, right, or 1,000 dictionaries, and you're still only going to have to search down the length of the word, which is great. Okay, not based on the size of the dictionary. No need to balance, right? There's no balancing here, right? Because the max depth is based on the word length, we're not going to worry about like, oh, we're going to have to go way down the tree. It doesn't exist anymore, right? Okay, so the complexity is 01. Perfect. Woohoo! This is why this is a cool data structure, right? Because it's our first one that we're like, whoa, we really get constant behavior for a lot of this stuff. Okay, pretty cool. Pretty cool. Okay. We are in that case ignoring the letter like comparisons, but that's kind of what we handle with this guy, and it's just going to add another constant factor. It's not going to be anything more than that. Okay. All right. What I said was the tree does take up a little bit more space, right? You can actually compress a trie, I should say. You can compress a trie, and I'll show you how to do that. I know a student who's a senior now who had an interview question where they asked her to produce a compressed trie, and she actually did pretty well on it, supposedly. But I'll show you what that actually looks like. Sometimes this can take up more space than a regular tree. Okay, so if you're worried about space, sometimes this isn't the best way to do it. If you're worried about complexity, this is a great way to do it. Here's how you can compress things. Right? If there's no follow-on characters, just have each node have the whole word in it. Right? If there's no follow-on characters. Yeah, Alex?
Oh, isn't that how some files are compressed? If you use like LDW compression, where like you take like patterns and just clump them together?
Yeah, right. That's how some compression algorithms work. Sure. Yep, where you use patterns of words and do it. But in this case, you could compress this. We can actually compress this even more. Right? Where's a case where we could probably compress things a little bit more even, like where there's no branches basically. What is it? Yeah, CO and FI. We can even do better, right? This would be like a super compressed trie. Now, the data structure part with the array is trickier. You're not going to be able to quite do it as easy as like just check the character of it. You'd have to come up with some other like method for doing it. Yeah.
So in this, would a new word that didn't have anything off it start as a single node, and then it would break off as new words were added?
Yeah. Well, right. So if you put a new word in there that started with Z, like zoo, right? It would go whoop, Z-O-O, and that would be the word. And it would have a little asterisk on it because it's the end of a word. And that means the end of a word in this case. And that would be about it.
Why does this have 2 asterisks?
2 asterisks means, in fact, what I've done here is said, because pit and pits are both in the, so we can even compress it more. And pit and pits are both part of the dictionary in this case. So that's why I did that. Again, this is like more advanced, right? If you want to just do a trie, which is what the like lab is going to be like. And if you want to do a try in later projects, you're welcome to. You have to figure out if you're going to compress it or not. You probably don't want to because it is a little bit more work, but if you'd like to, you can. Yeah.
So if you wanted to add like cat or something, then it would split CO up?
Yes, it would have to split CO up. Yeah, you'd have to, because if you entered cat, it would have to split CO up because the C and the O are different. So it would go, there'd be another branch you'd have to figure out. Yeah, Cam?
Why doesn't it split the red and the orange? Like why does it?
Well, in this case, I haven't. The only word I've put in there is red. I haven't put any other R words in. So if I put the word RE in there, actually, it would just put another asterisk above that. If I put reds in there, it would put an asterisk. If I put, I don't know, 2 other R words, redder and reds or something, then it might break a little bit more. Yeah, then it will break a little bit more. OK? Other questions on this? Get the idea of a try, though. I won't go into too much more detail today, but when you see the lab, you'll get a feel for it. What's neat about this lab is it actually uses that online try thing, and you get the output of your lab goes on the web, and like you can see the try and see if it works. So kind of neat. OK, here's a little bit what we talked about here. First of all, if you take a look at the a string, you can actually take the string and some integer, and that gives you the position of the character at position I of that string. Right? They've actually overloaded the bracket, if you want to think about it that way. But for the word red, S0 would be what? R, and S1 would be E, etc. Okay, so that's how you can actually do that. Okay, so here's the kind of the search word for the try. Let's see if we can make sense of it here. Okay, so we've got some node, and the node is going to have one of these character arrays as well, right? It's going to say while the node is not equal to null, okay, we're going to search. Pretend this is an integer. We're going to search through the whole length of the string. S.length gives you the length of the string, right? And then we're going to set a temporary node to be the current find child. And find child is the one that will actually go and say which one of these. I'll show you that in a second. Okay, which one of these is there and does it exist? Okay. If it doesn't exist, like if it comes back null, you have not found a word, right? Okay, and then you just keep iterating through. And if you get down to you finish the whole length of the word, right, is there a word marker there? In other words, remember, we can search for things like, let's see, what's a good example here? Something that if we search for da, D-A, right, which might not be a word in our dictionary yet, it would get to the end of the word, and then it would look at A and go, A is not an end of word marker, so it's not a word in the dictionary, even though day is, D-A is not. Right? OK. So here's the find child. Oh, and by the way, sorry, here's the find child. First of all, OK, return true if there is a marker, return false otherwise. Find child just says return the children at the position character that we're talking about minus A. And that's that. Right? And so this is exactly what we talked about earlier about how we do that. So it's kind of neat that it actually works out that way. It's pretty simple, pretty fast, and good. Questions on tries? Yeah, Charlie.
The dynamic arrays, or excuse me, the arrays for all of the nodes, do you initialize them in the constructor for a node, or do you, are we using new?
Yeah, good question. Good question. Are we using new in here? Well, you do know that we're going to limit it to some number, right? 26, so you don't have to. You could make it so that it would be just an array of nodes. You would want to go and initialize all of them to null, though, so that you'd know that there's one there or not. Because you would have to use, well, it depends. If you do a, let's say it was a node star, I don't know, child equals node star child 26. I believe that would go and You're right. I don't think that would actually make them null. You'd have to go through a for loop and make them all null.
Yeah, but then, and then when you wanted to actually add a word at the children.
You have to use new to create the new node. Yes. Yeah. You'd have to use new node. You would have to use the new to create a new node at each children part or each child. Yeah. Good point. Good point. Yes. Yeah.
So when you use a new node to create nodes for the children after that array, which means you'll be implementing a tree, right? Or will you be implementing an array? Okay, for example, you have cow and corn. So you have C and then O and then you have to break it up.
Okay, hold on. Let's say we're putting cow in here. I didn't show you the actual insert, but let's say you're putting cow in here. Okay, you're going to start with a blank node that's the kind of the root, right? This would be C, right? O would be down here somewhere. Another node here, which would be O. And then it would have its own array of 26. And down here would be W. And that's how that would work.
Arrays of arrays of arrays.
Yeah, sure. Arrays of arrays of arrays. Which is why it takes more space in general. Because you do have a whole bunch of arrays. But really, it's 26 times the, for each one in there. And lots of words don't have characters associated. Like there aren't that many words with, well, there's no words with QR, for instance, right? Now you could make a dictionary that has those, but there's a lot of combinations that aren't in our dictionary because English is a fairly regular language in that sense. Okay? Those of you who speak English as a second language know it's not that regular, right? And those who speak English as a first language probably don't do too, but yeah.
Would it be helpful for memory to have those as dynamic arrays that start with maybe 3 and then expand if they need to be, or is that not?
Well, yeah, because that's a good question. Should they expand? Should we start them and have an expand function in there? It depends on word frequencies. T, for instance, is a very frequent letter in English. T is way down here somewhere. You're going to get lots of T's. So you probably don't want to play that game if you can help it, right? You could, but you're probably not going to save that much space. Now, I'm sure if you're worried about space or if you're Apple making it for your iPhone or something, you're probably going to think about those details. And you're going to weigh different options back and forth. But, yeah.
What happens, often, when you're typing on your phone, it has, say, type DED and said, do you mean did?
Yeah, good question. Yeah, for a try, let's go back to the regular one here like this. Yeah, I mean, if you typed, let's say you typed DEY instead of DAY, right? Well, so there's got to be some artificial intelligence in there to say, OK, well, you're down here somewhere. There was no DE. Is there any? Let's do a little localized search nearby. Go back up a letter, do a localized search. Hey, guess what? There's a word that's very similar to this one. And you have to write a little function that just compares words. You can compare the distance between words and so forth, right? By how many letters are different and so forth. So there's lots of you can go down that road very far. There's lots of different functions you can write to do that. Good question. Yeah, I'm not exactly sure the ones that they use, but there's people have done lots of research on those things. Yeah, good. Anything else? OK, so that's tries. You'll see these in the lab. Okay, you get to play around with them in the lab, and some of you may decide to use them on future assignments in the class. You guys are probably too young for this reference.
Wait, really?
No, you guys know it? All right. Somebody was telling me in the other class, somebody was saying they'd never seen Star Wars, any of them, or Empire Strikes Back. But what I wanted to ask was, what I actually did ask was, look, do you know the big reveal in Empire Strikes Back? And she's like, yeah, I know. So it's got to be a lot of fun to watch somebody who's never seen Empire Strikes Back, when they get to the big reveal. And then be like, well, you watch them, you go, oh, cool. Yeah, it'd be interesting. OK, so that's tries. Like the other day, we've got to kind of go on to another different lecture, but we're going to catch up today. I can almost guarantee it. Okay? We are going to start talking about these things called priority queues. Okay? Here's what we're going to do for the rest of the time. Let's see. I already talked about commenting deadlines. I've got a quick Unix tip of the day based kind of on a dictionary, because that's what we just talked about, tries, right? There's this program. I don't know if you knew this. And I graded a few people's homeworks and noticed spelling errors in their README file. And I if there was more than one, I took off points. If there was one mistake, I was like, look, make sure you spell check your README file. But most people had OK README files. But there's a little Unix program that will let you do this. Let's see. All right. Did I put the Declaration of Independence? Yes. OK. I copied from the internet the Declaration of Independence, right? What is this one? This is Declaration of Independence. Where does it start here? Here you go. When in the course of human events, et cetera, right? OK. And what you can do is you can run this spelling check program on it. ASPELL-C for the to check the Declaration of Independence. And what it does is it comes up with this thing and says, oh, look, sufferable is not a word. Well, according to their dictionary, I guess sufferable is not a word, right? And you can change it in here. You can actually tell it to change to some other word, right? And it's doing the exact same thing you were asking about. It's doing the exact same thing you were asking about, like suggestions for it, right? So there's got to be some data structure back there that it's comparing various words for, right? Let's say that we know sufferable is right. We can hit, whoops, what did I hit? Oh my gosh. I don't know what I hit. Well, anyway. Usurpations, right? I don't know if that's really a word.
It's a word.
It's a word. OK, ignore. Usurpations, ignore. Dissolutions, probably a word. Ignore. Endeavored. It's the British spelling. Remember, they were British, right? Back in the day, back then. OK, so but I'll probably say, hey, I'm an American. I'm going to change it to endeavored. And I hit 1, and it changes it, and it just went and changed it, right? Let's see. Harass. Maybe it was spelled with 1 R these days. I don't know. Anyway, you get the idea, right? And it allows you to do a cool spell check on this. In fact, you can actually, oops, exit. You can actually look at the dictionary. Where is the Linux dictionary located? Where is the Linux dictionary located? Dictionary file in Linux. What's that?
Australia.
It's not in Australia, I don't think. There we go. /user/share/dict. Oops. Let's see. cat/user/share. Nope, not there. Let's try the other one. It's probably not going to be. Oops. Whoa. Probably not going to be there either. /var/lib/ Nope, not there. I don't know where it is in this one. Let's see. Maybe where is the Linux dictionary in Red Hat? Where is the Red Hat dictionary? Maybe that's it. Looking for a dictionary file. It's got to be here somewhere.
It's in user share dict.
There it is. User/share/dict/words. Good job finding that faster than me. Good job. All right. cat/user/share/ what did you say? Hang on. There it is. And I'm just printing out all the words, right? So it thinks there's a lot of words. It thinks like ZY, ZZY, VAS is a word. Well, maybe it is. Some biology word or something, right? So you can, boom, there you go. The count of the dictionary, let's see. If we do word count of this, it is 479,829 words. So that's cool. Question?
If you run that on like a C++ file, will it only check your comments, or will it like freak out and try
I think it freaks out, because I think it doesn't know your C++ parsing. Yeah, it doesn't know that. Yep.
If you tried to run it on an executable file, will it check the couts?
No, it'll probably just fail. Temp C. Why are you making me check this?
Well, no, couldn't you just type the output from it into cout? Into Excel?
Couldn't you just type the output? Oh, you could type the output, sure. But the question is like a spell -c and then hookbook abilities. This is going to be ugly. Yeah, there you go. See, it has no idea that it's not a text file. Yeah, so that's that. But maybe there's other spell checkers that would do that, but this one won't. OK, questions on the spell checker? OK. All right. Debuggers. Quick little note on debuggers. So I've showed you the Eclipse debugger in here a number of times. There is a command, if you're like dead set against using Eclipse, fine, be that way. You can use this other debugger called GDB. Go learn how to use it. It will allow you to do everything that the Eclipse debugger does. It won't give you a nice fancy graphical interface, but you can find out where your program's crashing. You can set breakpoints at various lines. You can look at the data structures and so forth. So if you want to do it, GDB is the way to go. I won't teach you about that because it's not worth doing in the class. It's a big hole. But if you want to learn it, go look up GDB and how to do basic stuff with it. Yeah, Jordan.
When I try to use GDB, like it'll work a lot of the time, and then it'll tell me there's like a missing library.
Sure. Yeah. If many times it will. So if you don't do it correctly and you try to step into a function that it doesn't know where the source code is, it'll give you that error. Generally, you can step out of the function and be okay. But if you don't, it won't step into functions that you don't have the source code for. That's pretty much it. Yeah. But it'll still work. It's just you got to figure out how. Okay. All right. Next thing we're going to talk about are these priority queues. Okay. Sometimes, one of the things we haven't really talked about in a data structure is this idea of what if we want to store data based on some priority? Now, we kind of do that with a tree. The priority is like the numerical order or the alphabetical order. But sometimes we don't want to. We want to have the difference between what we're storing in the data structure be different than its priority. Okay, so examples in real life for this sort of thing. Emergency rooms, right? I mean, you walk into the emergency room and you're like, oh, I think I broke my elbow falling on the street. And then somebody else walks in and is like, oh, I've got this knife sticking out my neck, right? There's a bit of a priority there, right? I mean, the priority is that guy gets helped first and you sit in the waiting room for 4 hours, right? Because it's all prioritized. And that's the kind of thing we want to talk about. We don't want to say, well, your priority is like when you walked in the door. Right? Because that would mean lots of like people with, dead people with knives sticking out their necks, right? Because they never get served. You don't want to be like, 4 hours like that, right? Office hours, right? Like, so we're in office hours. There might be a little priority for that, right? I might be talking to you, and then some professor walks by, or the department chair walks by, right? Guess what? Your priority just went down a little bit. Like, I'm normally pretty good about like, hang on 1 second to the professor, but normally we'll stop our conversation and we'll talk to the professor, right? Sometimes like a phone rings in, somebody was in my office hours today and had their phone ring and they were very nice and just turned it off and didn't even look. It was awesome, right? So that's like, if you're gonna be sitting with somebody and talking to them, don't like answer your phone and say, hold on a sec, especially if it's a professor. Now it might be the other way around. I did the exact opposite to that person. I actually did answer the phone, right? But it wasn't my cell phone. It was like the actual phone. I had no idea, But anyway, but there's priorities in these things, right? So we can do that. Getting on an airplane, oh boy, talk about priority, right? The airplane thing, I mean, who knows how you get on? There's like 17 different ways you can get on an airplane before other people these days, right? You look at your boarding pass and it's like, oh, I'm in zone 2. And you watch like 100 people get on before you and you're like, zone 2, what does that mean? Nothing, right? So it's so there's lots of different places where we have priority. And we want to disconnect the priority from the thing. Okay? So a priority queue has this idea. Okay, takes this idea and puts it into in an abstract data type, basically. It stores elements according to the priority and not in any particular order. Under the covers, there's going to be an order generally, not always, but generally there's going to be some order. But we don't care about that from the abstract data type point of view, right? It's not based on like a position. It's just based on your whatever the key that you're using a priority. Okay, no real notion of position. Okay, we're not going to worry about position anymore. Okay, yeah, question.
Does the priority of some element within the queue, can it change or is it always constant?
Yeah, you can change the priority. We have to be really careful when we do that based on the data structure, but you can change the priority of something. Sure. Yep. Yeah.
When it says external position is basically gone,
Mm-hmm.
it still kind of exists because you would know that you would say like the person third and fourth, right?
Yes. Now it turns out this is very much like a stack or a queue where you only can get one priority out of it. But yeah, under the covers we know that. But as far as the outside position, we know one thing. We know somebody's got the highest priority. That's all we know. So that's when I say there's no, and under the covers there doesn't have to be a position. Well, the handout I have will show you that in a sec too. Alex.
So like it's not like there's a line of people. It's like almost like a waiting room, like just this massive.
Yeah, exactly. It's like a waiting room, and could the person with the knife sticking out their neck come up, please? And And then there's 4 people with knives and whatever, and you got to prioritize those even more. But if you ever go into like the medical field, you will learn all about prioritization of like who gets treated when, and it's sometimes surprising too. Okay, so because we're trying to differentiate the priority from the thing that we're putting in this object, what we do is we say we're going to give everything a key. Okay, every object is going to have a key, and that's the priority. Okay, so it's basically like we're taking the key and we're tagging along some data with it. And the key is what we're really concerned about inside the data structure. Right? Keys don't have to be unique. Most of the time they are. They don't have to be. Right? 2 keys can have different data. Like the same key can have different data associated with it. It gets a little weird when that happens, but you can do that. For instance, you could have, let's see. Well, I mean, like I say, you could have two of the same things have the same priority. You have to then decide what the priority is. Most of the time, we just say, well, it's random at that point. 2 people walk in at the exact same time with knives stuck out of their head. The first person that gets to the front is the one that we go with, right? I mean, that's kind of the randomness of it there. Keys aren't necessarily unique, and can change. This is the question, right? It can change. You can. If you have a Yelp rating for your restaurant and all of a sudden you start like serving horrible food, right? Well, you're like the priority of what Yelp puts up on your puts up as your rating can go down, right? And that's what that's what we're talking about with terms of keys. You have to be really careful when you're putting in and taking out to change things, but we'll get to that. Okay. All right. A couple more details on this. Keys can be of more than one value. Like, for instance, if you're on a standby list for getting on a plane, if you happen to be in the frequent flyer program and like really an elite status, you're probably going to get on the plane. If you just bought your ticket and paid the cheapest price because that's what the online thing told you, you might not get on the plane, right? Priorities, like the key, can be based on different items. But you have to make those decisions when you design the database that you're talking about. Okay? You can generate the key based on a property of the book. So let's say you have the price of a textbook might determine how Amazon ranks you or something like that, right? Actually, Amazon's an interesting case. Have you ever gone online to like Amazon and looked up an item and it's got like a 5-star rating, and then you dig into the ratings and there's like 2 people ranked it? Right? Like that's probably not the one they should show you first. Just because the one below it has a 4.2 star rating, but 1,000 people have bought it, right? That's the one they should show you first. I think Amazon's got it backwards when they rank things. In fact, they might have changed it recently, but at least the previous times I've seen that. There's a big issue with like how do you do these priorities based on, you can't just base them on the overall score, because it's got to be weighted by how many people have actually like ranked it. So that's an issue. You can, so you can get this key generated by the property of the object. You have to be kind of careful with that. If the property of the object changes, the price drops or something, then your key might drop if you're trying to do it. And in some cases, if the price dropped in your data structure, you've got some key, and then the 2 things don't line up, you might lose the item in the database. Like all of a sudden you're searching by the key, and then the book price changes, well, then you're in trouble. So you have to be kind of careful. We'll get to those details in a little bit. Yeah.
Does your priority refer to like the actual order of these items, or some value stored in that item?
Well, right. It can be determined by whatever property it is. It can also be determined by something external to the item itself, right? So but it's not based on. It's not always based on like the data itself. It's just they are separate entities. Your key and your data. You can sometimes generate the key from the data, but not always. I mean, it's a long answer to say sometimes, right? Okay. All right. There's some details here that I don't want to spend much time on, but comparing keys is actually an interesting problem, because sometimes it's easy for numbers or letters or things that we can turn into a number, but as long as you can compare items, then you have to follow a couple properties involved with that. Again, don't stress about these. I'm not going to ask you these properties. But we have to be able to say things like an item is either less than or equal to itself, a key. Less than or equal to itself. This is like a kind of, if you ever take like a logic class, you'll go into these sorts of things. Okay, that's called the reflexive property. Again, no need to worry about the details of some of this, right? We've also got this property if k1 is less than or equal to k2, if key1 is less than or equal to some other key, then it's got to be true that, and k2 is less than or equal to k1, well then they have to be equal to each other, right? Like that kind of makes sense, okay? If k1 is less than or equal to k2 and k2 is less than or equal to k3, then you have to know that k1 is less than or equal to k3. You can't write your key comparison such that this would be a property that doesn't hold. In other words, okay, again, it's easy with numbers. It's not a big deal. If the comparison rules are satisfied, you won't contradict yourself. And this becomes really important when you're trying to order the things inside whatever structure you're using. Okay, we'll get into those details later. Again, just wanted to show you that you have to follow these rules if you're coming up with your own comparison, like to get the key, okay, or to compare against keys. Okay. And what these comparison rules do is they say, here's the order of the keys. The only difference is if two keys are the same, you might have them swapped, right? Because in whatever order, because you don't know. Like you can't take a difference between two keys that are the same. So they might be swapped. But otherwise, they're going to be a linear relationship between them. Which means that you can always have a smallest key, right? It could be multiple of the smallest, but you will at least have at least one smallest key, right? That makes sense? Aha. So if we have, yeah.
Does that mean, wait, by smallest key, does that mean that there are multiple levels of priority? As in more than two?
Yeah, yes, there's innumerable levels. You can be a priority 1, 2, 3, 4, 5, 6, 7, all the way up to 1,000,000. Right? I mean, all the way up to whatever, infinity, right? You can prioritize based on that. But all it just means is you look at all your keys, you're going to be able to pick out at least one of them and say that one is definitely the minimum. And there might be shared minimums, but at least you can find one and say this one is a minimum. Nobody will disagree that that's a minimum. Okay? So what is this priority queue? It's another container, just like what we've been talking about before, like containers that hold stuff, right? It has a key that you provide or compute when you insert into this data structure, and the keys determine the priority when you remove them. Pretty simple. This isn't like rocket science, right? It's like you put an object in, it's got a key. When you take it out, the keys determine what the priorities are. Yeah.
So let's say this function gives you this key, and you put your key into the function, returns some sort of value. Then the set of all the values is just a queue.
The set of all the values is the priority queue, yes. But they have their key associated with them. Okay? All right, so we can do operations. Just like any other abstract data type, we have these operations we define. We can insert an item into the priority queue. We have to give it the key or calculate the key, and we give it the actual element. That's the data part. Okay? We can then say min element. It could be max element, depending on the way you've ordered things. But you can't get anything in between. And in general, you don't do both. In general, you do either the min or the max. Lots of times, we'll just stick with the min. And the min element returns the element with the smallest key, which we know we can pick out. Okay? And then you can also do remove min. This is kind of like the difference between top and pop. Like min element just kind of tells you what the minimum element is. Remove min takes it out of the data structure. Okay? So those are the big the big functions we want to do. We also have lots of little functions. We can say how big the priority queue is. We can say whether or not it's empty, right? We can get the minimum key, which is interesting. That's different than the minimum element, right? The minimum element doesn't necessarily tell you what the priority is. It just says that's the one with the lowest priority. You can also say what the minimum key is, right? And don't worry about the constant reference. It basically means you can't go and change the key. You can change the element if you wanted to. You can't go and change the key. Okay? I say it's important, but I mean it's important only that when you're trying to get a key, you don't want to change it intrinsically. Yeah?
What if you have multiple minimum elements?
If you just get one, and you don't know which one you're going to get.
Just a
Random one. Yeah, in general. I mean, underneath the covers, something's deciding which one it gets. Probably the next one in the array or whatever it is that we're doing that. Yeah. Okay. All right. So priority queues, again, are simpler than sequences. It's a lot like a queue and a stack in that they're easier to deal with than all these other operations, right? You don't need insert before, insert after, add index, all those functions, right? You need one insert and one delete. That's it, right? The remove min and the insert. That's about it. Yeah?
Do any of like the NQ, DQ stuff apply to priority queue?
No, we don't have it. We're going to use separate terminology for this, right? Just remove min is the only one we need to do to remove it. Okay? All right, here's your example. This is the sheet you have. Anybody still not have the handout? Okay. It looks like that row is where they start. Go ahead and hand those back. If you need more, we'll get more. Okay. The handout you have, actually, you don't really need to look at it quite yet. But the handout you have is the program that I used to make this output. And it actually does the output exactly like this. So if we have a priority queue and we insert item A with a priority of 5, okay? The priority is 5. The key is 5 in this case. And the item is A. This is what our queue looks like. It's a little parenthesized, like this is the element, 5 comma A. Priority is 5, the element's A. Right? Okay? If we insert 9, then we've got 5A and 9C, and they're in there. Okay? If we insert 3, notice, right, in this case, we don't care what the ordering is. Okay, we'll get to when we might care about that. But in this case, we insert 3, now we've got 5, 9, 3. Okay, this is not like hard stuff yet, right? If we insert 7, we've got 7. Okay, so we insert all those guys in there. And then maybe we'll say, what's the min element? Well, if you look in here and you go min element, okay, so the one with the lowest priority in this case is 3. The element is B. What you get back is B. Right? You don't take it out. It's still in there. You don't take it out. If you say, what's the min key? It tells you, oh, OK, the minimum key is 3. Right? OK. If you remove the minimum, notice 3 is no longer there anymore. It's gone through, it's found the minimum, and it goes whoop, and it's gone. Yeah?
Will the key always be an integer?
No, the key won't always be an integer. You'll have to, most of the time it will be, because we normally care about that. Sometimes it could be whatever comparison you have. So if you have a comparison that follows those comparison rules, it can be whatever you want. The key can be whatever you want. Okay? Yeah?
So if one of we have the last homework with the class,
Mm-hmm.
would the fact that someone's a major or not would that be a priority?
Someone's a major or not, that could be. I guess you could have that being a priority. Yeah, you could. I mean, I would think of it more like this. The priority queue would rank them as to who's highest on the wait list. First person to get into the class. That's probably your priorities more than just your major. You could have 2 levels of priority if you want. Charlie?
What kind of information do you implement? What kind of implementation do you do to generate the keys? Because you're going to need to find information about each of these people. Like,
Depends. It depends what you. Yeah, it depends what you do. Many times, you if you insert into a queue and you don't give it a key, it might say the priority is whatever the next number that's above the max. But that's probably not the way we do it, only because you don't necessarily know what the max is. We'll talk about how to insert into a priority queue when we get to details. And by the way, this is all set up for a really cool data structure like next lecture. Not this, but we'll get to something this time. Yeah?
Can you have keys that are comparative to the data that's in there?
What do you mean?
So like, say, going back to like the emergency room one,
Yeah.
if like the guy with the knife sticking out of his neck is currently top priority,
Uh-huh.
and then the kid with broken foot is bottom, and then someone comes in that has, I don't know, no, like
They poured acid on their eye.
poured acid on their eye, and like so
Not deadly.
It would be top priority if it was just 2, but comparative to the people that are there, they're middle priority.
Yeah. You totally can rank priorities, right? In fact, you have to make sure that your data structure allows for enough distance between priorities. If you're just doing integers and you have 5 and 6, you can't put a 5.5 in there. Then you have to
But if you don't know, like, it's like you know you have stuff in your queue.
Yeah.
You do it comparatively without, like, can you tell it to find me a key that, like, I don't know how you would set this up, but comparative to what's in there, as if you didn't know what was in your
I'm not sure I understand. Talk to me later about it. I'm not sure I understand what you're trying to get out of this. But let's just get through the end example. The min element A. Now the min element's A because 3's gone. right? Remove min, A is gone. Remove min again, 7's gone. Remove min again. What if we tried to do remove min again? We get an error, right? And is empty is now true. OK, so those are kind of the functions here. All right. How do we implement this? The reason I gave you the code was so that you could take a look at the function, so you don't have to keep looking up here. And I numbered the lines. If you look at line 85, all the rest of it's like the beginning stuff. But this is the structure we're going to use in this case for an unordered list that's a priority queue. OK, it's going to be just like the one we just had on the previous slide. It's going to be unordered, and it's going to be a priority queue. Yes?
Why is the struct declared inside the class as opposed to just inside that? Does it make a difference?
It does make a difference. It means that a priority object is only part of a priority queue unordered list.
So in other words, by including it,
we're
you get priority objects, but only the priority objects that are already members of the class.
Yes. Yeah, you can't.
Instead of they can't make their own priority.
Right, right. You can't have some other function, other class making its own priority object. Right. It's just it's a scoping issue. You try to keep things nice and scoped. Yeah. OK, so this is what it is. Look, it's pretty easy. It's got a key and it's got an element. In this case, the keys are ints, the strings are elements, just like what we saw on the previous page. OK. All right, if you jump down a little bit to line 92, you start to go into the rest of the declaration. Pretty simple. I've just defined a whole bunch of functions here. Size is empty, insert item. Notice it takes a key and a string, min element, min key, etc. I've also got a print in there, so it prints it nice and pretty. OK. If you jump down to the private part on line, what is that, 103, right? We're using an array, just a dynamic array. We're going to have an expand. We're going to have a size and a capacity, all the stuff we've known for months now about dynamic arrays. Okay. The data structure we're using for this is a dynamic array. The abstract data type is a priority queue. Okay. Insert item. Haha. How do we actually insert item? Well, we actually it's really easy if it's an array that's unordered. Where do you put it? At the end, right? So easy, right? You put it at the end. And how do you do that? First, you expand if you need to. Then you just go to the size, and you put the key there, and you set the element of the priority, what was it? The priority object element to E. And then you increment the size. And what's the asymptotic complexity of this? Constant, right? Woohoo! That's great that it's constant priority, or constant insert. Well, how do we find the minimum element of an unordered list? What do you think?
We would have to go through all of them and keep track of whether they were lower than one that we've encountered before.
Yeah, you have to go through every single one, right? And this is what this does. Notice it goes from first it sets the first one, and it kind of skips the first one because you know either the first one is or you got to compare it against the rest. But it goes through all of them, and it just checks, right? And then sets the update. We've gone through this exact function before with arrays. I don't know if you remember that, but we did. And then returns the minimum index. What is the asymptotic complexity of that? Order n. Ah, that's not so good, right? All of a sudden we have order n behavior again. Ah, darn. Yes?
Could you have a queue that stores its minimum as you're putting them in? So that way it only checks before it enters, like if it's lower than the current minimum?
What's that? That's a what? You would still have to go through everything if it's not ordered.
But like as you put it in the queue, like as you put it in the priority queue to begin with,
yeah.
check it stores if it's lower than your current low.
So it's its own min.
Yeah, but then when you remove it, you have to go through all of them to update the min. So you're like, yeah, that's a good idea, but then you still have to do it later. You're never going to get past the idea of doing an order n behavior at some point or not, right? Now, if you happen to be doing concurrent processing, maybe you could send the min back and then in the background do the recalculating. But yeah, you still have to do it at some point. Yeah, good question though. Good idea. But can't quite do it in as much as you want to. OK, so that is order n behavior, not so good. We have a min element which actually calls the min index. The only reason I broke this up was to show you later that this doesn't have to change for a different implementation. But what it does is it just returns the element at the minimum index. Okay? So far so good? Okay, order n behavior. Boo. What about remove? Remove min. Yeah?
You would have to, well, once again, search the entire thing.
Search the entire thing, find the minimum.
Find the minimum.
Yeah.
Or, wait, the minimum?
Yeah, it's removing the minimum.
Oh, the minimum reduction, okay. Yeah, remove
Yep.
the minimum.
Yeah. And then what?
Well, remove the minimum that's closest to the front anyway.
Yeah. So, well, remove the minimum that's closest to the front. There's only one minimum, let's say. Oh, I see what you mean. Let's say there's only one minimum right now.
All right.
Okay. So there's one minimum, and we're going to remove it. Let's do a little. Just put a little example on here. 4, 8, 2, 7. Remove min. Well, let's make it. Let's do one more. 12. Okay. Remove min. You've got to go through this whole list and find the minimum, which is what asymptotic behavior. Order n. So then and then it knows, hey, I'm going to look at 0, 1, 2, 3, 4. It's at, oh nice, it's at index 2 is our value. Okay, if I want to remove it, what do I have to do? Change everything back? So I would have to make 7 go here and 12 go here? Look at the code and see what I do. Look at the code right here. What have I done? I've just switched it. Because it's unordered, I don't care what the order is. I'm going to get rid of that one. I don't want an empty space. I don't want to move 7 there and 12 there, because I don't have to in this case. I can just go, hey, 12, you move over here. In fact, I can even leave the 12 there, and I'm updating the size, and it'll be fine. So altogether, order n behavior again. Yeah, Maggie.
What if it's the last
If it's the last element, you don't do anything. You would basically, yeah, this is one where you'd say this one equals this one,
Okay.
right?
Okay.
Yeah. And
But
oh,
because
hey,
you
guess what?
size.
Guess what?
What?
Huh, interesting. Remember how I said you never want to do A equals A? Like you never find a case where A equals A? That's exactly the case, where A equals A. And if your if your assignment overload didn't check for being the same one, you would crash. Very interesting.
Wait, it would crash?
Yeah. If your assignment overload, now in this case we don't need an assignment overload, but let's say these were objects. Well, they kind of are. Yeah, very interesting. You've just figured it because people ask, when would you ever do that? This is exactly the case where you do that. Interesting. Okay. So, but order n behavior, not so great again. Boo. In the unordered list, what did we had 3 different things. We had insert, we had remove min, and we had remove min, and we had index. Let's see. Sorry, we had min index and we had remove min, right? Or I guess it was min element and remove min. Okay, and they were order n and order n and order 1, right? Not amazing. Inserting great, getting the min out not so great. Let's do this instead. Let's make it an ordered list. Okay, so let's keep it ordered every time. Then it's going to be great, right? Let's find out. If we do an ordered list, and that's the other ordered list on your thing, right? If you go to 130, that's the next place we'll go to. No, sorry, that's unordered list. Ordered list is all the way down on 269, line 269. What we're going to do is we are going to, as we add elements, we're going to keep the list in order as we go along. Okay? So before we said it was like 4, 8, 7, 12, and 2. Let's do it in a different order. Let's do it 4, 8, 2, 12, and 7, let's say. Okay? As we do this, if we put the 4 in, it's going to go here. And then we're going to put the 8 in, and it's going to go here. And then we're going to put the 2 in. Well, we have to do a little bit of work, right? Because we need to then figure out that we have to move the 4 and the 8 there and the 2 there, right? This is, yeah. What's that? Oh, sorry, you're right. The minimum is going to be, yeah, in this case we're going to do it the other way around. You're absolutely right. And according to the code, that's what we're doing. We're actually going to put the minimum at the end in this case. So 4, and then 8's going to go in, so it's going to go 4, 8, and it's going to be downward. You're absolutely right. And then 2 is going to go in there, and that's going to be here. And then 12 is going to go in, and 12 means we have to move all these guys. So we're going to have to do a little bit of work, right, to do this. Well, it's not too bad. It's not too bad. It's called an insertion sort. When we talk about sorts in like a week and a half or so, the first one we'll talk about is an insertion sort again. Okay, well, one of the first ones. And this is where it starts on line 270. If you go to like the next page, it's the most of the rest of it. We have to do this like math to keep this going. Here's how I did it. There are a number of different ways to do this, right? But in this case, we said, fine, for I is equal to the size of the array and then go backwards through it. It's probably easier to go backwards through it than to go forwards through it because we're going to have to move elements that way. And going backwards makes it easier to do that, as it turns out. Okay? And so what we're going to do is we're going to go down until the key is the one that we want. So let's do this again. We'll put 4 in there, 8 in there, and then 2 in there. So it's going to be 8, 4, 2. And then let's put 12 in there. Let's put 7 instead. So it'll actually make it a little different. 4, 8, 2, and then 7. If we put 7 in now, what we're basically going to do is go to 2 and say, does 7 need to go on the other side of 2? Like, which one's bigger, 7 or 2? 7 is, so we have to keep going this way, right? And then, sorry? Well, let's see. Does it move 2 when it does that? It does move 2, yeah. So it says, OK, 7's going to be, 2 is bigger than 7, so 2 has to go here. OK, 7 is bigger than 4, so 4 has to go here. 7 is less than 8, so 7 can go right there. And that's when it breaks out of the loop here, when it finds that 7 is now less than 8. OK, and then it puts the 1 there. So that's how an insertion sort works. It goes through, finds the place, and moves everybody over in the meantime until it gets to the right place where it needs to insert it into. Okay? Is it a good type of sort? Not the best. We can come up with much better sorts, but for now it's going to be an easy enough one. Okay? What is the asymptotic complexity of this? What is it? Why is it n? You might have to move everybody, right? So the worst case is n. Right? The best case is constant, right? And the kind of the average case is basically n. I mean, n over 2 if you really want to think of it that way, but you don't really know. So in this case, it's order n. Yeah. OK? All right, so this is order n. Boo. We thought we were going to do better here. We've got an order n. Right? Not so great. That's all right. We're OK still. What about min index? That's easy. It's ordered. We know the minimum index is size minus 1. Right? Return it. One operation. Woohoo! Right? Same thing for the min element. Remember how I said this was not going to change? Min element's exactly the same. Return the priority queue of the min index. It's the min index part that was before it was asymptotic complexity of n. Now it's asymptotic complexity of 1. Woohoo! Right? That's great. OK. How about remove min? You don't have to do anything. You just have to change the size, right? If we're removing the min, size instead of being 4 is now 3. You're done. No moving, no swapping, no anything. That's awesome, right? So keeping an ordered list is good. We lose out on the front end, gain something on the back end of this. So here's the bottom line. For our ordered and unordered priority queues, we got to make some trade-offs here. Can someone give me a case where I might want to use an unordered list based on this? Ben, what do you think?
One that would involve lots and lots of insertions?
Yeah, and very few removals. Yeah, that's very good. Was that what you were going to say too? Yeah, same thing, right? Absolutely. You've got to do lots of insertions and not so many removals. That's a good way, yeah.
When would you ever have a situation where you just want to throw data into a structure and then never look at it again?
Right, that's a good point. Many times we don't want to do that. Although maybe you do want to, you might want to have this big database and then you're very rarely going to look at it, then you never know. You never know, there might be that case. Well, it's there to be looked at. Yeah, that's true. It's a good point. Yeah.
If there's a function that you can print out the list, then you wouldn't necessarily ever need to use min element or remove min. So that would make sense to work.
If you're printing it, you said?
Yeah. If you like.
Oh, yeah. Well, if you're printing it in order, you would need to use both. You'd need to use both, right? If you're printing in order, you need to print one, you print the min and then remove it, then print the next min and remove it, print the next min and remove it, etc.
If it's implemented in the class, then you just use the.
Yeah, but that's no longer a priority queue anymore. It's now just an array, right? It's not a priority queue anymore. Yeah, Charles.
So in each of these implementations, we'd say the asymptotic complexity would be linear for both of them. However, in different situations, then it would be preferable for either case. So
Yep.
in economics, there's expected payoff. Is there expected asymptotic complexity?
Is there? Well, you don't. If you know, only if you know your data set, right? You still have to know your data set first. But like we said, if there's a case where you're going to do lots of insertions and only a few removals, maybe you need to do that. Here's another example. Let's say you're inserting 1 billion items and then you just want the top 10. Well, that might be a case where doing the unordered might be a better idea, right? I mean, there's probably better ideas than that even. When would you use an ordered list? Yeah.
For not so many things, but a lot of checking.
Well, yeah, or if let's say you're Apple and you want to create your database and you can do that on your servers, then you just upload it to the device and then never have to recreate the data set. Yeah, an ordered list is great because then you can actually search it, binary search if you had a list. Priority queue, you can just, you can take a look at that. Yeah?
Would it be at all helpful to have like a situation where you switch between an unordered list and an ordered list,
Yeah, once you're ordered, you're not going to want to go back. I mean, once you're ordered, there's really no reason to go back.
like there was a time where like you knew you were inserting a ton, and then like after that it might be less, and then you want to switch to
Yeah, you would just do a sort, right? You'd say, okay, now I'm going to sort my data. And that takes time, same sort of thing. Yeah. Oh, yeah, takes time.
Kind of ends it because you have a thing that sorted itself after every 5 insertions. So like.
Yeah, could you sort it after every 5 insertions? Sure. I mean, yeah, you could. You could. There'd be trade-offs there. What's that?
I wouldn't think that would be any faster.
It depends on the use case, I suppose. I mean, you probably wouldn't want to do that. You'd want to either sort at the end or sort, But maybe if there's a downtime in your system, you can say, hey, go sort it because it's not sorted yet. I mean, things like that. Yeah, there's various ways you can do that. But again, there's trade-offs here. Now, let's see. Do I have anything else here? No. There's trade-offs here. And next week, we will learn how to get better behavior from a different data structure than making this horrible trade-off where some of our behaviors are order n. OK? Great. I'll see you guys next week.